Hello, everyone. Welcome to the session. Today, we're going to discuss disaster recovery strategies for streaming. So just a quick intro. I'm Shashidhar. I'm a specialist solution architect in Databricks based out of Amsterdam. I have Sachin with me, who is a solution architect from London. So this is a high-level overview of what we're going to discuss. So we'll spend some time on why disaster recovery strategy, why it is important, what does the stats say, and we'll focus on what are the different disaster recovery strategies that you can use for your streaming pipelines. And then we'll focus on how do you pick the right strategy depending on the type of streams, the type of workflows that you have, and the type of transformations that you're doing in your applications. And finally, we want to show two use case demos, which broadly covers most of the streaming use cases that you will be generally implementing using structured streaming. Yeah, let's get started. Okay, the overview. So why disaster recovery matters? So there are many surveys and statistics, and it's quite obvious, like if you're in a highly regulated industries, you should have a proper disaster recovery strategy, because 80% of the time, disaster has occurred across all the data centers. And failures are costly. Depending on the type of the business that you're in, you cannot really have failures in your system, and the downtimes cannot be long. If you don't have a proper strategy, the downtimes can be long, which will affect, again, back to your business, not just from the technical standpoint, but also from the revenue standpoints as well. So if we look at the high-level disaster recovery process, so these are the sequence of events, what you would have seen in any DR process. So typically, there will be a backup, which will happen frequently. That is taking the snapshot of your data, some of the statuses, application data, or whatever. So by the time you take the backup and the disaster occurs, so we call this as recovery point objective, which defines, depending on the strategy that you choose, how much data loss that you are okay to have in your business. So the idea is normally RPO should be lower, because we should not be having a lot of data loss, because that will again adversely affect your business. And then the disaster event, from the disaster event to the failover, so this is the duration which is represented as RTO, which is nothing but the time in which you bring your secondary environment back to life. So these are the two key factors which basically drives your DR strategy. How do you do the DR and how do you address it? And then we have the failback, which is nothing but once the primary is back, you just move over to the primary when you want. So why streaming apps have a special case here? Because streaming is a continuously running application, and it always have a context, right? Like for example, Spark streaming tracks the state of your ingestion, depending on the transformations, maybe the state of your aggregations, everything in checkpoint. So it is important to track, it is important to back up not just the data, but also the context which is tracked in checkpoint directories. So having a consistent backup across all the different layers of your data pipelines, for example, starting from bronze to gold, is a challenge, because some might be falling back, some might be up to date with each other. And for stateful streams, there is a special case where the state itself is persisted into the checkpoint, which is, again, you need to have a special mechanism there. How do you deal it? And doing all this, we have to minimize the data loss when the DR happens. And also, we should be able to automate this so that you have a proper disaster process in your system. So I will leave at this. I'll give back to the Sachin to go over the strategies.
Thanks, Shashidhar, for giving an overview of disaster recovery. And next, what we'll do is we'll go through a specific use case. And for this, I'm going through a role play. And let's assume that I am a chief data officer of a bank, and we are implementing a specific use case to detect and prevent fraud in real time for the payment systems. For this, we have adopted Databricks Lakehouse architecture. And in this Lakehouse architecture, we are sourcing different kind of data, such as the payments, real-time payments coming from different channels, customer data, as well as past fraud reports coming from third party. Now, as we ingest all this data, it lands into our bronze layer. We do some parsing as well as some curation, land into silver, and then we create features which are kind of an aggregates required for the fraud detection. And these fraud detection algorithms are run in downstream machine learning training programs as well as the inference programs. So for this architecture, we need to have a really robust disaster recovery strategy which meets our strong RPO and RTO requirements at an optimum cost. For this, defining or choosing a right disaster recovery strategy needs careful consideration of the business requirements. And there are three key parameters, I would say: the RTO, RPO, and the cost. Shashidhar already explained what is RTO and RPO, and I'm not going through that. But these are the key parameters. One can achieve the best of the RTOs and best of the RPOs. However, if the cost is very high, that's not really good. So as a business, we are looking for the balance between these three parameters. And let me just give you a quick overview of our business requirements. So as part of this, we would like to have no data loss, because this is our payment system for the banks, and RTO, which is time to recover and catch up. It can be a couple of hours, and we would like to optimize the costs. So that are our those are the main business requirements from our side. So for this, we have brainstormed multiple disaster recovery strategies, and we have came up with these 4 disaster recovery strategies. First one is the multi-site active-active, wherein it is operational on the primary site as well as the secondary site. Next one is the warm standby, where one is active, another is passive. And we would like to reduce the cost and improve the RTO and RPO. For that, we have come up with 2 additional variants of active-passive. Those are clone bronze and clone all. We'll go through each of that. The first one is the multi-site active-active. So in this strategy, primary site as well as the secondary site is operational and continuously running the data. So in this approach, we are processing data in primary site as well as secondary site. In case of disaster, we just reroute the request to the secondary site. This gives the best of the RTO as well as RPO. However, this is most complex and costly solution. I have seen very few customers going with this approach because this is really costly. So let's go to the next one. So next one is the warm standby. So warm standby approach is active-passive. Here we are running continuously into a primary site, and secondary site is executed on demand. So in this case, what we will be doing is, in the primary site, we are running structure streaming job in a continuous mode using micro batches, whereas in the secondary side, we still source the data from the sources and keep it ready there, and every night, let's say in our use case, every night we'll just recompute bronze, silver, gold in our secondary site using some specific trigger. In our case, we'll go with available now. So this is active passive strategy, and this reduces the cost. However, the RTO and RPO are still a little bit on the higher side. In the next strategy, what we are doing is, this is as I said, it's a variant of active-passive. So the first strategy is clone bronze strategy. Here, it is bronze table is copied or the backed up into the secondary side, and we are not ingesting data from the source systems. And from bronze, we recompute silver and gold. So this is the bronze strategy. I'll go into the details later in this, but this reduces the cost because we are not ingesting data from the source system, and data is already in the bronze layer. So this is about the clone bronze strategy, and the next one is clone all. So in clone all strategy, we are not recomputing silver and gold. Rather, bronze, silver, and gold, all three layers are backed up from the primary system. This, one of the main difference between clone bronze and clone all is clone bronze works for stateless as well as stateful, whereas clone all works for stateless. So we'll go into the details of this. So this is a summary of it. Let me go to the next slide. So this is the summary, wherein, as I said, active-active, best RTO and RPO, however, cost is on higher side. Warm standby is active-passive. The cost is on lower side, but RTO and RPO are little bit on higher side, and we are trying to optimize the RTO, RPO as well as the cost using deep clone strategies. So with that, I will hand it over to Shashidhar, who will go through what are deep clones and how we can use these deep clones for disaster recoveries.
Thank you, Sachin. So before we start the use case and how we are doing this DR, so let's spend some time on understanding how can we pick the right DR strategy. So in any DR, like there are different components that you have to consider for backup, right? So if you are dealing with streaming applications, of course, data is obvious one. You have to back up the data from the primary to secondary frequently. But along with that, we are also doing something called backup of the offsets. So what are offsets? So if you have used structured streaming in Spark, so it runs in micro batches, right? Like the Spark structured streaming. So every micro batch will basically track the offsets of your source tables and commit them into checkpoint directories. So we can use this information and understand how much of the data has been processed in primary when we run the backup. And when we're taking the backup, we actually clone the exact version so that we're not really duplicating the data in the secondary if we want to fail over. So let's see how it is done. So first we'll figure out like how do we track the offsets, right? So if you have used structured streaming, if you have debugged any issues with the streaming with Spark, so there is something called query progress logs. So they normally give you the insights about what has happened in a particular micro batch. So here you can see there is something called sources, which basically represents what is the offset that is being fetched in this micro batch and how much it has processed when the micro batch completed. So if you see the right-hand side, we have start offset and the end offset. And in the bottom, you have the delta table, right? So delta table, we know like we have multiple versions for every commit. So the micro batch is nothing but it will pick some of the commits from your delta table, process it, and it will write to the sync table, right? So in this case, this particular micro batch has processed from version 4 to version 7. So, and this information is also checkpointed into your checkpoint directory. So we can use this as a basis of how do we track the offsets when we are doing the backups. So let's go to the data part. So for the data backups, we normally recommend deep clones for delta. So deep clones is nothing but an efficient way to back up your data, and the good thing about deep clones is incremental. That means if you are running the clone again and again, it will only pick the changes that has happened at the source table so that it's not really cloning your full data set every time. So let's see how the deep clone works. So this is a time series view of multiple clone operations, what we have triggered. So just for the sake of example, let's say we have bronze, and we are cloning the data from bronze to bronze clone table. So you see on the bronze, we have 3 versions, and every delta table has a unique identifier, which is the ID, what I'm showing. And if you're running the clone now, you see on the T0 that we have created a version 0 in the bronze clone table, which has the exact snapshot of the data from your bronze. But the thing that you have to observe is we are losing the history of the delta table. So basically, the whole 3 versions of your source table is collapsed into one version whenever you run the clone, and the data is identical, but you're losing the delta history. So to make it more clear, if we see the T1, we're running the second clone, but this time we have 2 more versions in the bronze, like 3 and 4. But when we are running the clone now, we create 1 more version in the bronze clone, but it will just have the changes that has happened in the source between 3 and 4. So the clones are incremental, but whenever you run the clone command, a new commit is persisted into the delta history table, into the delta history. And one more thing, if you can observe here, is the clone table has a different ID. That means the clone delta table in itself is an independent table, which has nothing to do with what is happening at the source, unless you trigger the clone again and again. So if we see what is happening at the streaming side, and if we associate it back to the deep clones, so I'm just opening up one of the checkpoint directory here, and you can see the table ID of this particular stream is registered or persisted into your checkpoint folder physically. So that means if you clone, the checkpoint becomes obvious. That means you cannot really reuse the checkpoint on the clone table. So if you're using deep clones, you cannot really just copy the checkpoint and resume your streams back in the secondary. So to summarize, if we see the broader category of streaming apps, you have stateless streams and you have stateful streams, right? So in the stateless streams, the assumption is you are not using any stateful operators in your applications. So you can clearly go with clone all strategy, where you can take the deep clone backups of every delta table in your pipeline. But if you have a stateful stream, you have to recompute that particular step in your pipeline. So that's why we are going with clone bronze strategy here. So with that, let's start to see what we are doing with the stateless streaming pipelines, right? So this is a typical architecture what we have seen for majority of the customers at Databricks. So you have bronze, silver, gold. Mostly until the silver, you propagate the data in append-only manner. And then from the silver to gold, you aggregate the data. You can do it in multiple ways. So in this case, we are using for each batch, and we are doing the join and merge into the gold table. Or you can do it in a different way in this architecture, something like this. So here, basically, you are doing streaming until silver, but from the silver to gold, you are running a batch job. So this it really depends on your application. Some use cases are okay with having to run the batch job between silver and gold, depending on the type of KPIs or the type of aggregations that you do. But both are basically stateless pipelines with respect to streaming. So if you have a stateless pipelines, the recommendation is to go with clone all strategy, which is basically cloning all the tables periodically and keeping track of the offsets, so that whenever the disaster happens, you can resume from the same point in the secondary environment. So let's see how we are doing this. For the demo purpose, we are basically using the fraud detection use case what Sachin mentioned. So let's assume we are ingesting some data into bronze using autoloader. And then from bronze to silver, we are filtering some data quality checks. And then from silver to gold, we are running a for each batch to do the aggregations. The use case here is more like if you see a lot of transactions per hour, so there is something wrong with this, with respect to this customer. So with this, let me go to my notebooks. I can show you like how this use case looks. So this is our pipeline, where we are basically having 3 streams. Towards the end, you can see ingest to bronze, bronze to silver, and silver to gold. And this is an end-to-end pipeline, so we are doing the ingestion as for the demo purpose. Pretty straightforward. There is nothing strange. So only thing what I want to show is in silver to gold, we are doing a for each batch. Just for the sake of tracking which batch ID we are committing into the delta table, I'm doing something called, I'm using the option of this. I'm using the metadata here, if you see, which is nothing but the user metadata, which goes into the delta table history of your destination table. So this will help us in, in the DR process. So let's say, we want to introduce the DR, like we want to make the DR to happen. So what I'll do is I'll go to compute. I'll just stop the cluster which is running this job. Yeah. So let's understand what we are doing as part of the DR process first, and I'll go back to the backup job and explain. So we are running the backup periodically. What it will do is it will find versions of your each table which is processed until gold layer. So here, for the simplicity's sake, let's just say that we have 2 versions in all the 3 tables, and all the data is processed until gold. So we take the backups now, and we also take the versions and the corresponding versions between the tables, between bronze in primary and secondary, and between the silver in primary and secondary. So that we can start the streams in secondary using the property starting version if something goes wrong, which is the DR. And in the DR, like in the secondary, when we are doing the failover, we're not reusing the checkpoint. We're just starting with brand new checkpoint, and we are just specifying the starting version so that it will just pick up the new data that gets committed into your source delta tables. So let's go to the backup job so that I can show you like how the backup job looks. So it's a periodic job. Depending on your source and sink, for example, in our case, we have source for the raw to bronze. The source is autoloader. We are loading the JSON files. And every other stream, the source is delta table. So depending on the source and sink, how we track the offsets differs. And that's what we are doing here. So at the end of the backup job, you can see, we're tracking offsets of each stream. I'll just zoom in a bit. So you can see the bronze offsets, it says the source is, this is a CSV file. So we're tracking the file names for the first stream, which is a raw to bronze, which is an autoloader job. So this is the latest file that is ingested into the bronze. And the sink for this bronze stream is a delta table. So that is having the latest commit of 6. So similarly, for the silver, it's a delta to delta. So you can see the source is 6 and the sink is 5. So these are nothing but delta table versions. And for the gold, you have source as 5 and the sink as 2. So you can see like the bronze sink is actually equal to the source of the silver stream. So which is nothing but your multi-hop pipelines, where it is basically representing the fact that the data is progressed until your gold layer. So there is nothing in the source which has to be processed at this point. So the backup job we have already executed, so I'm not going to run this again. So let's go to our primary and see what happened there. Yeah, so we are seeing all the jobs have failed because I just crashed my cluster. It says like, cluster got terminated. So now what I want to show you is how do we resume this from the secondary, right? So before doing this, I just want to show what are all we are tracking. So one thing I want to show is So this is my secondary database. I have bronze transaction table, gold transactions, silver transaction, and I also have something called offset tracker. So this is where we are basically tracking the offsets whenever we take the backups. For every backup, we create a new entry in this table so that when the DR happens, we can use this information and start the streams from the offsets as we want. So if you see the data here, so it has the ingestion file name and every table version and its corresponding secondary table version. Yeah. So let's go to the secondary job and try to resume this because my primary job has failed, so that I want to start my secondary job so that it can ingest the new data whenever it lands. So I'll give it some time. I'll explain like how we track the offsets a bit. So for every stream, this is what we are doing. We go to the sync table and we see what is the latest version in the sync table which has the highest batch ID, like the micro batch ID, which will tell, that is the latest batch ID which has committed to this delta table. So using this batch ID, we go back to the checkpoint directory and understand what are the corresponding source versions it has used to commit this data. So this is how we link the source versions and the sync versions, and we just clone them using the information we get from this, the workflow which I explained. And once we clone, we also track what are the corresponding versions of the tables in the secondary environment. So finally, we create this entry in the offset tracking table, what I showed earlier, and this is what we'll use to resume the streams. So let's go to our secondary job and see what is happening. Yeah, so we are getting the data. This is my secondary job, and you can see we have ingested some new data, and it is processing from the point where it left. So just to make the things clear, I'll go to the secondary database and show you the tables, and you can understand what is happening. So this is my gold table in secondary. Yeah. So you can see there are 2 clones initially. So this is part of the backup job, and then everything else is a merge command. So this is the merge command, what I'm running from the for each batch. So this basically started just now, like the new secondary job which we triggered. And the clones are basically what we have ingested the data when the backup has run. So we're not really reprocessing all the data when we're doing the failover. We are just ingesting the new data which is not yet ingested in the primary from the time the backup has happened. So in this way, we are basically avoiding the data loss, like the RPO is basically 0. We're not losing any data. We are just resuming from the same point when the DR happened. So I'll quickly wrap this up. The only aspect I want to touch is how do we do the reverse backup? Like when the primary comes back, what we have to do. So we just have to switch over our backup process. We take the backups from secondary to primary, and then we clean up the checkpoint directories in the primary, and we start the streams in the primary with starting versions. So with that, we kind of went through the full life cycle of the DR, which had the failover and the failback using deep clones and the offset tracking. So I'll give it back to Sachin, who will go to the next use case.
Thanks, Shashidhar. Now, what we'll do is, this works really good for stateless transformations. However, as Shashidhar was saying, we cannot use the checkpoint in the secondary. So this approach doesn't work. The clone all strategy doesn't work for stateful transformations. So for stateful transformations, what is the other option? So this is a specific use case where same payment information, the real-time payments which we are ingesting, instead of doing stateless transformation, let's assume that between silver and gold and bronze and silver, there are stateful transformations. It can be something with window operations with watermark. Now, in such use cases, what we will do is we will go with clone bronze, and in clone bronze strategy, this is the same slide which I showed earlier, but I will go much in detail here. Here, I will just back up the bronze table using deep clones and from the primary region to the second region. However, the silver and gold layers I am not cloning, rather I will be recomputing. So, for this particular use case, what I am doing is I am taking the backup of the bronze table every 4 hours. Let's say this is our business requirement, so 4 hours is good enough. However, we are recomputing silver and gold every night. In case of disaster, what would happen is your bronze layer will be few hours behind the primary, whereas silver and gold will be maximum a day's data will be behind primary. In case of disaster, I'll start ingesting data directly from the source in the second region, and in this use case, unlike clone all, the checkpoints are not cleared. So, whenever I start this pipeline in a continuous mode, it will go into the checkpoint and it will start from the same point where it stopped last nightly run. So, that's how it runs, and for bronze, we are anyway having the offset tracker, and we'll keep track of the last file, and whenever we start ingesting, we'll not process the same file again. We'll start processing the next file. So, that's our approach. This is just another view of the bronze clone bronze strategy, where the backup is taken every few hours, whereas the recomputing is done in silver and gold every night. With that, I'll quickly go through the same demonstration. So, if you see this pipeline here, this is my primary pipeline, same as what was happening in the previous use case. The only difference is here we are having stateful transformations between silver and gold. In case, apart from that, what I am doing is I am taking backup. So, this pipeline is already running, and I have already executed the backup job. So, this backup job will run every few hours, every 4 hours. So, this is scheduled to run every 4 hours, and the only bronze table is cloned in the secondary region. So, I have already done this cloning, and the additional part is nightly run. So, in this case, I have scheduled to run recompute silver and gold every night. So, every night I will just recompute silver and gold from the bronze. However, I am not ingesting data from the source. That is where I reduce the RTO and RPO. Other point is here, as I said earlier, I will be reusing the checkpoint. So, we are not clearing the checkpoint. Checkpoints are maintained, and whenever we start next day, it will start from the same point or same offset which left last night. Now, let's say a disaster happens. So, in case of disaster, primary site is down, and we have this pipeline in the second region. In this pipeline, we are sourcing data from the source system which is ingested into the bronze, and we are going into the offset tracker. We are looking into the file which was last processed at the time of backup, and we are starting from the next file. So, that's how we are not ingesting any new files, and then bronze to silver and silver to gold runs from the same offset. So, there is no duplicate reprocessing. So, this is our pipeline which we are running at the time of disaster recovery. So, with that, I will just go back to the slide. So, we have covered all these 4 approaches, and we went deeper into the 2 approaches which are mainly based on the clones. And let me summarize this. From this presentation, I would like you to take 3 key points. The first is deep clones. Deep clones are the best for backup of the delta tables And if you are having any disaster recovery strategies, you should be using deep clones. The second is, if you are having stateless pipelines, clone all disaster strategy provides the best SLAs at an optimum cost, and this is highly recommended by us for all the stateless pipelines. The third is the clone bronze strategy. So the clone bronze strategy was mainly cloning the bronze, but at times, as Shashidhar was explaining, even from bronze to silver, there are mostly like stateless transformation. You can actually generalize to clone bronze, clone silver as well, and wherever there is a stateful transformation, like from silver to gold, that's where you can recompute the gold layer. Having said that, as it needs some nightly reprocessing, there is further work required to optimize the cost the way we have done for stateless transformation. So with that, I'll just close the presentation. Thank you very much, and we are open for questions.